All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is gas laws part 3. You are going to need a calculator for this one, so if you don't have one handy, go ahead and pause the video and we will get started. We want to focus on two laws. The first one is the combined gas law, and the second one is the ideal gas law. The combined gas law, P1V1 over T1 is equal to P2V2 over T2, allows us to look at two different situations. So a situation 1 and compare it to a situation 2. Where either the pressure or the volume or the temperature or some combination is going to change. The ideal gas law, PV equal nRT, is for a specific situation. In other words, the situation is not changing from one pressure or volume or temperature. It's remaining the same, and you simply want to know one of the variables. You must know the others, but you have to know all the others, but it allows you to know one of the variables. So let's, with that in mind, take a look at the practice problems. I want to just point out that R can be of two different values. It's going to depend on what the pressure is measured in. If it's measured in atmospheres, we're going to use 0.0821. If it's measured in kilopascals, we're going to use 8.314. So with that, let's go ahead and get started. Let's look at number 1. It says, how many moles of helium are in a balloon of a volume of 6.452 cubic decimeters at 99.7 kilopascals and 297. All right, first of all, let's make a decision as to whether or not we're going to use the combined gas law or the ideal gas law. So remember, the ideal gas law is for when we have a specific situation. We're not changing from one to another. We have a specific situation. So we wouldn't use the combined gas law this time. We're going to use the ideal gas law. We're not going to use combined. We're going to use the ideal gas law. So what is the ideal gas law? It tells us the pressure times the volume in any situation is equal to the number of moles of gas times the universal gas constant, R, and it could be either of two possibilities depending on what pressure is measured in, times the temperature. We're looking for the number of moles of helium. I've underlined that. So number of moles of helium is equal to PV equal RT. That's pretty simple algebra. Just bring the RT underneath the PV. And now let's start plugging in. N is equal to, the pressure was given to us as 99.7 kilopascals. The volume, 6.452 cubic decimeters. Don't allow that cubic decimeters to throw you off. A cubic decimeter is the same thing as a liter. So essentially what we have is kilopascals times liters on top divided by, we're going to use the R value of 8.314 because we've been given the pressure in kilopascals. So the unit for the 8.314 universal gas constant is going to be the liter kilopascal per mole per degree Kelvin. And then we're going to multiply that by temperature. It has to be in degrees Kelvin, and it is. That's 297 Kelvin. So when we solve that, we multiply the two numbers on top divided by 8.314 divided by 297. We get this number, 0.261 to the correct number, significant digits, and that will do it for us for number 1. Let's take a look at the second problem. The second problem says this. It says a rigid 8.77 liter tank. The word rigid means that we are dealing with a volume that's not going to change. That's what rigid means. So a rigid 8.77 liter tank contains 1.45 moles of oxygen at 20 degrees Celsius. What is the pressure in atmospheres? We're going to have to remember to change that 20 degrees Celsius to Kelvin degrees. Remember, the temperature must always be in Kelvin degrees. So here we go. The ideal gas law says that PV equal nRT. Again, we're not moving from one situation to a different situation. So this is not the combined gas law. We're dealing with the ideal gas law. The ideal gas law says this. It says that pressure times volume is equal to the number of moles of gas times the gas constant times the temperature. So let's solve then for the pressure, because that's what's being asked. It says, what is the pressure in atmospheres? So pressure is equal to nRT divided by V. So let's plug in. Pressure is equal to 1.45 moles times the gas constant. Notice this time we're given the pressure in atmospheres. So we'll use 0.0821 liter atmospheres per mole per degree Kelvin as our constant. The temperature is 293. I just added 273 to 20 to give me the temperature in Kelvin. So 273 plus 20 is 293 divided by 8.77 liters. That gives me a pressure of 3.98 atmospheres. Remember, if you use the 0.0821 liter atmospheres per mole per degree Kelvin, the pressure will be in atmospheres. So that'll do it for number 2. Let's look at the third problem. Number 3 says this. What is the temperature of 12.2 moles of gas in a 18.35 liter tank at 16.4 atmospheres? Express your answer in both Kelvin and Celsius degrees. So here we go. Again, we're not moving from one situation to a different situation. This is not the combined gas law. We're simply taking a snapshot of a gas. We're given certain variables and then asked to find something else, in this case temperature. So we're going to use the ideal gas law. So the ideal gas law states that pressure times volume is equal to the number of moles of gas times the universal gas constant times the temperature. We're solving for temperature, so let's rearrange. We have PV, pull the RT underneath, pull the NR underneath, the NR underneath. And so now let's plug in. We get 16.4 atmospheres, that's the pressure, times the volume is 18.35 liters. We'll divide that by the number of moles, which is 12.2 moles of gas. And we're going to use, because we have pressure in atmospheres, 0.0821 liter atmospheres per mole per degree Kelvin. When we do the math, 16.4 times 18.35, we'll divide by 12.2 and then divide again by 0.0821. We get a temperature to the correct number of significant digits of 300. Notice the decimal, that's 3 significant digits. Those last two zeros now count. 300 K. If I want to know this in degrees Celsius, I'll simply take the 300 K and subtract 273. When I do that, I get 27 degrees Celsius. That'll do it for number 3. All right, let's take a look at number 4. Number 4 says the volume of a gas is 200 milliliters at 275 K and 92.1 kilopascals. Find its volume at STP. So in this case, we're dealing with two different situations. We're dealing with non-standard temperature and pressure conditions, and we're dealing with standard temperature and pressure. So here's what I need you to know. I need you to know that standard temperature and pressure is 0 degrees Kelvin and, 0 degrees Celsius. 0 degrees Celsius and 1 atmosphere of pressure. 0 degrees Celsius and 1 atmosphere of pressure. So the combined gas law then tells us that P1 V1 over T1 is equal to P2 V2 over T2. That's the combined gas law. So pressure, volume, and temperature relationship in one situation is equal to the pressure, volume, and temperature relationship in a different situation. Now we're looking for the volume at in a second situation, what we call STP. So V2 then is equal to P1 V1 T1 divided by T1 P2. Let me say that again. V2 is equal to P1 V1 T1 divided by T1 P2. Let's plug in. V2 then is equal to, the initial pressure is told to me to be 92.1 kilopascals. V1 is 200 milliliters. V1 is equal to, T2 is equal to, that was V1, T2 is equal to 273 Kelvin. Now what I'm going to do is I'm going to divide that by T1, which is 275 Kelvin, and 101.325 kilopascals would be P2. When I solve for that, I get 180 milliliters. So the volume at STP is going to be 180 milliliters. All right. Now notice, by the way, that I didn't change the volume from liters to from milliliters to liters. Just remember, if you're using the combined gas law, if you start with milliliters, you're going to end up with milliliters. You don't have to convert it. I recommend that you do, by the way. But if you elect not to, just remember with the combined gas law, if you start out with milliliters, you're going to end up with milliliters. Okay, you can't do that, by the way, with the PV equal nRT equation. You have to convert that to liters. But for this one, it's okay if you leave it in milliliters. That'll do it for number 4. Let's look at number 5. Number 5 says, what pressure in kilopascals is exerted by 94.6 grams of CO2 at 57 degrees Celsius in 0.750 cubic decimeters. All right, the first thing that's going to happen is we're going to have to convert that gram value into moles. So what I'm going to do is I'm going to say 99.6 grams over 1, or 94.6 rather, grams over 1. If you add up carbon plus 2 oxygens, you get 44.01 grams per mole, right? So these two units are going to cancel. Grams and grams are going to go away, and I'm going to be left with 2.15 moles of carbon dioxide, all right? So now I know the N. We're not moving from one situation to a different situation, so we're going to be using the ideal gas law here, PV equal nRT. So the ideal gas law again is pressure times volume is equal to the number of moles of gas times the universal gas constant times the temperature. So let's solve for P. We'll simply divide both sides by V. We get nRT divided by V. So N is equal to 2.15 moles times R is 8.314 liter kilopascals per mole per degree Kelvin. Notice I'm using kilopascals, so I'm going to use the 8.314 value times the temperature. The temperature is 330 K. I've simply added 273 to 37 to give me the 330 K. Remember that the temperature must be in degrees Kelvin, and then of course the volume is 0.750 cubic decimeters, right? All right, when I do the math, I get 2.15 times 8.314 times 330. We'll divide that by 0.750. By the way, a cubic decimeter is the same thing as a liter, and when I do that math, I get this number, 7870. That's 7,870 kilopascals. That'll do it for this one. And let's go to the final one. Number 6. It says a sample of propane occupies 250 liters at 125 kilopascals and 38 degrees Celsius. We're going to have to change that 38 Celsius to Kelvin. It says find its volume at 100 kilopascals and 95 degrees Celsius. So obviously we're going to be using the combined gas law here. P1V1 divided by T1 is equal to P2V2 divided by T2. So now we're looking for V2. So V2 then is equal to, we'll just rearrange to give us P1V1T2 divided by T1 divided by P2. So V2 then is equal to 125 kilopascals times V1 is 250 liters. Remember, you can leave it in liters, and you don't have to change to milliliters. It's already in liters. Times 368 Kelvin, right? 368 Kelvin. So you have to change temperature to Kelvin, divided by 311 Kelvin, divided by 100 kilopascals. That'll give us V2 of 370 liters. All right? That'll do it for number 6. That'll do it for this worksheet. I'll see you on the next one. Thanks. Bye-bye.